Okay, let's get started here. So today we will continue talking about PCA. We'll also come back to project number 1 a little bit. If you have not received approval from me for your project number 1 data, please make sure you get that data to me so I can approve it. Are there any questions before we begin? Okay. So we were talking about the goblet data. And what we're interested in doing is, let's say, finding the true dimension of the data. And what that means is that we have basically 5 different measurements of these goblets. And we like to see, do I really need to, let's say, know those 5? Or maybe the true number of things I need to know is something less than that. And then also we like to be able to come up with some, you can say, natural groupings of these goblets. What we found is that the first 2 principal components, these new variables, explain about 90% of the total variability of the data. What that means also is that it explains, let's say, 90% of the information that's available in the data. That's quite high. That's good. And that says to us, hey, maybe this true dimension is only about 2. With 3 principal components, we get up to 95%. And the way that these principal components are formed, as a review, is that we look at the eigenvalues, the eigenvectors of the corresponding covariance matrix. So the first, corresponding to the first eigenvalue, meaning the largest eigenvalue, we have this particular eigenvector. To form then the first principal component then, we'll call it y hat 1, is that we basically find a linear combination of this eigenvector with our mean adjusted variables. So here's that 0.758, that first component of that eigenvector. We put 0.75 there, 0.758 there. We multiply it by W1, subtract off its corresponding estimated mean. And we do that throughout. Here's 0.036, 0.036, W6 minus its corresponding estimated mean. And so once we have these principal components, then, well, we like to be able to interpret them. And so with this particular principal component, we can see that, for those first 4 variables there, I have a positive weight on them. For the last variable, I have very little weight at all. So what that means is that essentially, since the first 4 variables correspond to the width of the goblet, basically this first principal component is telling us information about the overall width. Then principal component number 2, notice that we have the first 2 values in that eigenvector are positive. The last 3 are negative. Those last 3 are for the base. The first 2 are for the top of the goblet, the cup portion. So what we're doing here is basically forming a contrast between the top and the bottom. Okay. Now we had just got done talking about a scatter plot of the principal component scores. Meaning that we take, let's say, the equation that we just saw, we plug in the actual values for W1, actual values for W2, and so on. And then we plot that first principal component. We do the same for the second principal component, and this is what we got. And so, for example, let's see, principal component number 1, again, remember, corresponds to the overall width. And we can see that we have some observations that tend to have a higher width, and also the top of the goblet seems to be large comparatively to the bottom of the goblet. That's my interpretation coming from principal component number 2. And you can make other interpretations for these other, you can say, groupings that we essentially kind of form. Now these groupings, some respect could be up for debate in terms of, well, should I really maybe separate these 2 groups, And that's okay. You know, there's not going to be usually one strict answer for a grouping when you're using principal component analysis like this. Okay, so that allows us to see the first two principal components. And while I'd be satisfied with just using two principal components, well, what if we did use three? What would our corresponding plot look like if I were to do, let's say, a bubble plot? And so I need to get this third principal component now on this scatter plot. Now remember, with a bubble plot, basically the plotting point is proportional in size to a third variable. We need this third variable to always be positive, so we can get that proportionality there. And so if we take a look at a summary of that third principal component set of scores, we can see that, of course, we do have negative values. So we need to make an adjustment. And simply all we do is we take all the principal component scores. So you might remember from last time, the principal component scores were stored in an object called score.chord2. So if I say comma 3 with the brackets, that means I want that third column, the third set of principal component scores. If I now subtract off the minimum of these third principal component scores, now all my values will be from 0 and up. So you might be thinking, wait a second, why am I subtracting? Well, notice if I subtract, and notice also I have a negative out in front. Those two, that subtraction, that negative becomes a positive. So in other words, I'm going to be adding 0.13839 to every single principal component score for number 3. So that's why I'm going from 0 and up. And so from there, it's a matter of application of what we learned in the graphics section. I use the symbols function, my x-axis, my y-axis. The bubbles correspond to the circles argument, and that's where I put in this new object that I found, PC3.positive2. And I can go ahead and do the plot. I'm going to use the text function in a similar manner to what we did with the scatter plot, so I can identify which observation corresponds to which bubble. Okay? And so the way that R is going to then plot it is that it's going to plot on the exact x and y coordinates for principal component 1 and 2. And this is what we get here. Okay. So we can obviously see we have some bubbles that are much larger than other bubbles. Again, the number that's in the middle corresponds to the observation number. That's the actual location of the x and y coordinates again. We can do one other small thing with this plot to make it better. How about we incorporate whether or not the principal component number 3 was actually positive or negative by actually colorizing the bubble. So to do that, create an object called call.symbol for the lack of a better name. I use the if-else function, we've seen this before, where I do a test. Is my third principal component score greater than 0 or not? If it is, let's assign a value of red. If it's not, let's assign a value of blue. And my code is exactly the same, except for in my symbols function, I now use the FG argument to allow me to get the color of the symbol in there. And now we have a plot that we can more easily interpret. Okay. So again, in a plot like this, we're looking for trends. We're looking for outliers. What do you think, or what do you see here? Well, let me get us started off. You remember this grouping that we had before? Well, this also kind of helps us see that they are similar to one another. Notice they're all blue. The bubbles are about the same size. Notice we have these red bubbles up there. So they have, again, similar characteristics. Again, now for that third part, this third part, this distinct part of the information about our data. And then we also see something else. Maybe we have some additional information here that we hadn't thought of before. Notice how those are all red, and the ones right above it are all blue. That's kind of interesting. So maybe we do have a different way of maybe grouping our data that we hadn't thought of before. I'm going to hedge on that. I think you'll see why coming up. So also another way to represent this in 3D is to do a three-dimensional scatter plot in the same format as what we've done before. Let me actually go over here to R to do some of this here.
Can I ask a question?
Sure.
You said, what are those numbers in the circles?
That comes from the text function. It's the actual observation number, experimental unit number. That's what those represent.
Because I saw there were like one number between two circles,
Hold on.
like 10, 3, and 16.
Okay. Yeah, thank you for pointing that out. So the number's in the middle of the circle. So 16 is definitely in the middle of one of those circles, as is 3. Well, where's 10 circle?
It's a small dot.
It's a small dot. That happens to be the middle. Yeah, I remember when I was going over my notes the other day, the first time for the section, I was like, okay, is there something wrong there? Am I missing 10? No, and I did verify that it was the minimal. Okay. Fortunately, I had to restart my computer here, so I'm going to need to get some of this information back into R. Okay. Okay, so again, we're going to use the RGL package. Maybe I did some of this out of order. In the end, it doesn't really matter. So to do a scatter plot, I can use the plot 3D function. And you can see that there's two different calls to plot 3D there. One of them is going to give me my actual, let's say, dots for the scatter plot. The other one is going to give me my needles for that scatter plot. So if you remember when we did do the graphics section, we said, well, basically you can draw, let's say, imagine, let's say, a plane in a 3D plot for the x-axis, the y-axis, I'm sorry. Imagine a plane in the 3D plot where the z-axis is 0, and we draw lines up from it to the point to help you see where those points are. Those are called needles. And so what I'm going to do here for plot 3D, x-axis, principal component number 1, y, principal component number 2, z, principal component number 3. And for some reason, I decided to start with the needle first. And so that's what that type equal h corresponds to. Now I'm going to use the same x-axis and y-axis limits that we had before. If you remember, we found common limits so that we could see the differences in the variability for the two principal components. And so if I do this, here we can see some needles have been drawn. Now to get the points, I use plot 3D again, where I say add equal true. Color is going to be red. The size of the plotting point's 6. Let's see, there it is. And if you notice those needles, some are going, you can think of it as going down, some are going up. It's because, remember, we have a principal component number 3 that can have positive and negative values. So if I do have a plane at z equals 0, some are going to go below, some are going to go above. How can I get that plane? Well, this is where I can use the persp 3D function that we've seen before, perspective 3D. We use that to draw a plot of the multivariate normal. Here I'm just going to use it to draw my plane. And simply what I'm going to do, for my x values that I'm going to draw, I use my common limits. In other words, there's the minimum, there's the maximum on my x-axis. Same for my y-axis. And now for z, if you remember the way that we had to organize the the information that we put in this function was kind of maybe different from what you normally think of. And so, basically I have something like this: min max of x, min y, max of y, and then basically we kind of form like a matrix. And I'm going to put all the z values at 0. So basically I'm kind of forming that kind of structure. If this isn't totally clear, go back to the data distributions and correlation section where we did draw these kinds of plots. And so when I add this then to the plot, I also put some grid lines. And in fact, I can also use a function called text3d to add observation numbers to it. This is what I get in the end. And here we go. So of course, I can rotate as needed. You can see that green plane there, that's at z equals 0. Okay. Now, what are some things that we can see corresponding to what we saw before? Well, notice where 24 and 23 are. Remember, they had basically, you could say, high values for all 3 of the principal components. Also, remember those clump of points that we saw before, 4, 5, and 17. Notice where they fall right there. And let's see if I can get this just right. Oh, I think this will work. Okay, let me relate this back to that bubble plot. So with the bubble plot, remember we have, for the stuff that's on the left, we have some stuff that has a red bubble. We have some stuff that has a blue bubble. Notice how the blue ones are kind of smaller in terms of the bubbles in comparison to most of the reds, not all of them. Okay, so we have like a narrow band, you could say. Well, let's look at that from a 3D plot perspective. Here are the blue ones. Here are the red ones corresponding to what we saw in that bubble plot. We can see something very similar there. And so again, if you think of like groupings, we're looking at differences amongst these points there that might lead to potential groupings. Okay. Now, as what we've seen before, sometimes I will add notes as I'm preparing for class. And I will put these in red. Now, in this particular case, I did not use common limits for the z-axis because I wanted us to see the differences better. So essentially, I'm kind of zooming in somewhat. But another perspective is perhaps I should use same limits, same z-axis limits. And let's see what would happen if I did that. Let's see. So I can use the argument zlim when I first draw that plot. It sets zlim to my common limits. And this is what we get. Okay. Do you see differences from what we had before? Why are they so more scrunched down, I guess, towards that green plane now?
Less variability.
Yeah, less variability. Remember, each principal component, well, principal component number 1 is going to have the most variability, 2 is going to have the second most, 3 is going to have the second most, and we equate variability to information about our data. And from what I said before is that I'd be okay with just 2 principal components. That third principal component is only giving me 6% or maybe it was 5% more information about my data. And so we can see that if we look at it from that perspective, are you really gaining much from looking at that third principal component? Maybe not. And so I guess from a teaching perspective, it's helpful for me to show you hey, you can see trends in those original set of bubble plots in the original 3D plot. But even if we did see those trends, are those trends really meaningful in the end? Because there's really not much information that's being explained by that third principal component in comparison to all the other ones. Okay? Yeah.
Or maybe I missed something here. We scaled the second piece, the third PC
Yep.
to not have negative values, but here we can see that we do have some negative values for.
Yeah, I just went back and used the original ones because it was only the bubble plot where we needed to do the rescaling. That was it. Any other questions? Okay. So, this data comes from some kind of archaeological site. But let's say, there was another archaeological site nearby, and it was a very similar culture that lived there long, long ago. And they want to take what they've learned with the original archaeological site to this new one to come up with classifications, to come up with groupings for these goblets that they found and find the new one. So how could they take what we just done here to this new site? Well, what they could simply do is use the predict function to now use the eigenvectors that we had previously, use that predict function now to find scores for these new goblets that were just found. So, I do my original analysis that I had before with this original archaeological site. I save my results again in pca.cove. Let me make sure that I'm using the right one here. Yeah, it was in pca.cove. Okay, so now I have that. Now I can use the predict function. We've used the predict function before to find the scores for our original data. But now if I had, let's say, a new goblet, how could I use the predict function there? All I need to do is say predict object equal pca.cove, and then use the argument new data. That makes sense to call it that. And have a data frame. I decided to call it pred.set for the lack of a better name, predict set, where in pred.set, I have the same kind of structure to this new data that I have with my original data. So I have a W1 variable, I have a W2 variable, I have a W4, W5, and W6 variable. And just for illustrative purposes, let's say that this new goblet that we found had exact same measurements as the first goblet in the original data set. So that's why I have goblet 2, 1, comma there. I put those actual values into this new data frame, and I use predict with it, and we get exactly what we had before. Okay? Okay. Let's talk about a little bit more about the calculations that are done in print-comp. So this is the original function that we use to, like, for example, calculate the eigenvectors. And you might be thinking, okay, well, we could just find the eigenvalues, find the eigenvectors by using the eigenfunction that we saw way back a few weeks ago. And yeah, you could do that. Well, once when I was going through some of these notes, I decided, well, I'm going to go ahead and do that. I want to verify that indeed that I'm getting what I'm expecting to get. And when I did that, I found out that my results were a little bit off. I thought that was strange. And so I had to actually go into the print-comp function, read what was going on in it to figure out why was I getting something different. And this is what I found out. So, back in your very first stat course, you learned about how to estimate a variance. You know, often you use the letter S squared, or you use S squared to represent sample variance, and you had some kind of expression like this. We don't have multivariate data here. You know, you take the sum of the x's, subtract off the mean, let's call it x bar, we square it, and then we divide by n minus 1. And so what we're doing here is we're essentially getting like an average value, an average squared deviation for your sample. And then earlier in our course, we learned the extension of that to a multivariate setting. Notice how I have the 1 over n minus 1 there. Now, does anyone remember why we use n minus 1 versus just n? You know, maybe the
Sample, your n samples.
Excuse me?
It's not population, it's sample.
Well, yeah, it's just a sample, but why don't we just use n? That's what I'm saying. Why don't we just use n? And the answer is kind of up there already. And that is, you know, your first stat course, your professor hopefully told you, well, it's because you're going to get a better estimate if you use n minus 1 versus n. It's a little bit more complicated with that than that. If you take a mathematical statistics course, you know, you would learn about how can you find the expected value of s squared, and you could actually derive it and show that it ends up being, let's say, the population variance, which I'm going to call sigma squared. That n minus 1 allows this to happen. Now, if I were to use what's more, let's say, intuitive, to just divide by n itself, because we are finding like an average value, then if I were to do that, you won't have that happen if I had, let's say, just n there. And you don't want that to happen. You know, it makes sense that, okay, you know what an expected value means. What would I expect on average if I were to go out and take a sample, calculate s squared, go out and take another sample, calculate s squared, go out and take another sample, calculate s squared. The average of those s squares, I would hope, if I did this many, many times, should be sigma squared. And you get there if you use n minus 1. You can prove that mathematically. But if you use n, you don't. You're a little bit off. So that's why we use n minus 1 versus n in the calculation. Okay. Now, I don't know why print comp does this, but they use it. People will often refer to this as the biased estimate of covariance matrix versus the unbiased estimate of the covariance matrix. In case you haven't heard that term before, unbiased versus biased. Unbiased means that if you take the expected value of a statistic, it's equal to the parameter it's trying to estimate. Bias means, well, that expected value is not equal to the parameter that you're trying to estimate. So, why were my calculations off if I were just to use eigen, that function? Is because I was using the unbiased version. Print comp uses the biased version in its calculations. So, now if you have a very large n, do you think there's going to be much of a difference at all between these two covariance matrices? No. I mean, even if you have a moderate size n, it's not going to be meaningful. So, in the end, there is not, notice the red text here, there is not a meaningful difference in the PC interpretations that you get, because again, you know, we'll be using the eigenvectors from the covariance matrix. There's not a meaningful difference in the PC interpretations and in the scores that you calculate. So because of that, we are simply going to use the results from print comp as is. But just always have that in the back of your mind that, okay, it's a little bit different from what we would like, a little bit different from how I originally had presented it. Okay? Any questions? Well, there are some, let's say, possible issues with principal component analysis in general. Some of this is just understanding exactly what PCA is doing. So I wouldn't really call it an issue, but I did decide to label it as an issue. You just have to understand what's going on. But also, there is one issue that you have to be careful about, and it's actually going to change how we typically do principal component analysis. Make a small change. First of all, if the original set of variables are uncorrelated, PCA will not help. Why? Well, PCA is meant to find, let's say, distinct or, yeah, we'll call it distinct parts of the information that your data gives you, okay? It finds uncorrelated new variables. So if I did so you could do this on your own. Suppose you found the estimated correlation matrix for these 5 principal components that we just found with the goblet data. You would find the correlations are all 0 between these new variables. Again, what principal component analysis is doing is finding distinct bits of information about your data. And so if you already started off with, let's say, x1, x2, x3, x4, x5, that were all uncorrelated to begin with, well, you already have distinct bits of information. So there's no reason to use it. PCA does not generally eliminate variables because the PCs are linear combinations of the original variables. So yeah, with the goblet data, we found that the true, let's say the true dimension of this problem, of this data, is actually essentially 2. But we can't throw away those 5 original variables because these 2 new variables that we're coming up with are all linear combinations of the 5 original variables. Now lastly, the original variables need to be measured in the same units and have similar variances. Remember, when we choose the number of principal components that we need, we look at the total variance that we get from the covariance matrix, and we look at the proportion of the total variance that a particular principal component explains. Let's consider the following scenario. Suppose I have 3 variables, x1, x2, and x3, and look at these variances that they have for each of them, respectively. So x1 has much, much more variance than x2. x2 has much, much more variance than x3. I could form, let's say, the first principal component like this. Let's just say I let that coefficient on x1 be 1, coefficient on x2 to be 0, coefficient on x3 to be 0 as well. So in the end, I'm just left with x1. Well, what's the proportion of variance then that I'm explaining by using this? 98%. So I could just form my first principal component like that and say, hey, I've explained 90% of my variance. I don't need anything more. That's the problem that one can have if, let's say, you have, let's say, data that's measured on totally different units. So x1 could be measured on a totally different units than x2, than x3. It might make sense then, well, for the variance to be 98 for x1, for 1.9 for x2, and so on. But that's going to screw up your principal component analysis. You'll see an example that comes up with the serial data. That the serial data, we have much different variances for the variables. And in the end, in the end, we get something like this. Okay. We don't want that because that's not helpful to us. So what's the solution then? Well, remember we talked about standardized data in the data distributions and correlation section. You know, one characteristic of standardized data, well, let's talk about two characteristics of standardized data. First, let's say we have Z1. Z1 is for the first variable. Z1 will have a mean of 0. Will have a variance of 1. Z2 will have a mean of 0, a variance of 1. So how about, instead of performing principal component analysis on your original data, you just use the standardized data? That way we won't run into the problems that I had just discussed there, where let's say one variable, let's say, dominates all the other variables in forming a principal component, because everything will now have the same variance. So we can use the standardized data, and you do everything that we did before, you know, where we use the estimated covariance matrix to find the eigenvalues, to find the eigenvectors. Now, we talked about how there's a nice relationship between the correlation matrix and the covariance matrix when we have standardized variables. First, the covariance matrix for standardized variables is exactly the same as the correlation matrix. If you're having trouble remembering seeing that, go back to our notes where we talked about that. Second, that correlation matrix that you get with the standardized variables is exactly the same as it is with the original variables itself. So because of that, people will often say, okay, I'm going to do a principal component analysis using my correlation matrix. So they will find the eigenvalues, they will find the eigenvectors of that correlation matrix and do the principal component analysis that way. But just remember, that's exactly the same as using your covariance matrix, again, like what we just did, but now with your standardized variables. Okay? Now, because of this problem with variables having different variances, most people will take this approach when doing a principal component analysis, always. Even if the variables are measured on exactly the same unit scale, like what we had with the goblet data, people will often use the correlation matrix. Now, that is the one place where it can make sense to use the regular old covariance matrix of the original data again. The reason being is because maybe you do want to take into account how maybe, let's say, W1 has more variability than W2. It might make sense in the context of a goblet that, okay, yeah, the top portion of the cup, if that has more variance, I want that to play a larger role in my analysis, because that top portion of the cup is, well, where I get the wine out of, or wherever you're using the goblet for. So that's what I just said corresponds to that there. Okay, so let's talk about the small changes that are going to take place if we use the covariance matrix from the standardized data, or equivalently, let's say, just use that correlation matrix of the original data. Now, our correlation matrix, we first defined it as a bold P. Again, you know, this is, let's say, the population correlation matrix. You're not going to know what that is in actual application. You're going to need to estimate it, and we'll call that estimate R. And the estimate was defined earlier in the notes. Now, to help differentiate then the notation then, when I am using R, my eigenvalues are exactly the same as what we had before when I was using sigma hat, except for I'm going to put a little star in the superscript for the lambda. So lambda again represents an eigenvalue. The hat there represents it's from the estimated corresponding matrix. The j corresponds to the jth largest eigenvalue. Now the star there is going to correspond to, now I'm using the correlation matrix. So you can see we have a lot of little notation. Maybe you've run into this in your own work, but there can be times where, let's say you have, let's say something on top of, well, let's use a different letter. Something on top of the letter that you're defining. You have something in the superscript. You have something in the subscript. But then you could also have, let's say, a pre-subscript. We'll call it a pre-superscript as well. You could go that far. Unfortunately, we don't have to do that here. Okay. So the corresponding now eigenvector that is defined the same way. It's found from the estimated correlation matrix. I put a star there. So notice the red here. I added before class. So what would then this first principal component look like here? So I'm going to put a line underneath the letters there to mean that this is bolded. That's what the first principal component would look like. So in other words, it would be something like this. Sorry, I shouldn't have a subscript there. Notice I'm using my standardized variable there. Since it's standardized, I don't need to, it's already essentially mean-centered. So that's why you don't see like what we had before, like x1 minus mu1. Then, of course, then the second one would look like this. And I kind of said this before, last time. There might be time. A great question on a test that should hopefully be very simple would be, okay, write out what that first or what that second principal component could be relative to your data itself. So what that means is you're going to use printcomp, get the output based upon what you see in the output, then you can write out or type out what that principal component would be. But the key is sometimes where students forget, we have to work with the standardized variables. So how do we determine how many principal components to use? Well, the first two are exactly the same as before. But now we have a third way. Find the number of eigenvalues greater than 1. Why should we be concerned about that?
There are the variance. Is the variance data.
What are the variances for these? 1. So, you're forming new variables based upon the old variables. You want these new variables to explain more information or explain as much information about the data as possible. Ideally, you would like them to explain, let's say, more information than what an original variable would have. And so that's why people often use then 1 as a cutoff. If I form, let's say, suppose I have a third principal component. We'll call it Y3 star. If that, remember that variance is going to be equal to lambda 3 star. I could put hats on it if I want to talk about estimates, but I don't think I need to. Let's say that this variance then is less than 1. Then it comes to, might make you wonder, well, why should I even form this new variable if it's explaining less information than one of our original variables? So that's why people often use this as a cutoff. Do note, no matter what, I will always look at that. And if I'm not satisfied with that being high enough, then it calls into question, should I use principal component analysis? Or also, maybe I should, let's say, if I do use it, say, okay, I understand that I'm not accounting for as much variability as I would like, but here are the results. What about PC scores? Well, we just use our same equation that we saw before, but now we put an R to represent, let's say, the rth observation on these corresponding Y's and Z's. And we can find the actual numerical values in the same way as before, but again, working with the standardized data. Now, we have to actually now go back to something that we talked about a few minutes ago. There is a small calculation issue then with print comp and using the predict function to find these scores. To find the score, R is going to need to find the estimated mean of the original variable and the estimated variance of the original variable. So x minus mu hat divided by that, what we would call the square root of sigma hat hat. I'm sorry, sigma hat, let's say jj for the jth variable. Or I could say r instead. R uses the bias estimate for that variance rather than the unbiased version. So because of that, the calculations will be a little bit different from the way that essentially I'm presenting it. Is it a big deal? No. But, and it's up to you if you want to use it, I will show you a little trick to get the calculation done correctly. Okay, so let's go back to the goblet data. So I'm going to create an object called pca.core to represent, hey, I'm using the correlation matrix of the original data. And I'm going to repeat myself here. Remember, that means I'm just using the estimated covariance matrix of the standardized data. The code is exactly the same, except for this part right here. Before we had core equal false. Now we're going to say core equal true, meaning correlation matrix. I decided to also put scores equal false there because I'm going to, in the end, use the predict function shortly. And so here's my corresponding output. So for example, this right here is the square root of lambda hat star 1, which represents the square root of the estimated variance of the first principal component. Notice, only the first two of these lambdas are greater than 0. So this is somewhat similar to what we saw before where, yeah, maybe 2 principal components is enough. And we could also look at the proportion of variance that these principal components are explaining. The first two principal components explain about 87% of the total variance in the standardized data. So again, I'm probably okay with, I shouldn't say probably, I am okay with just using two principal components here.
Why is less than the covariance?
It ends up being less here because if you look at that covariance matrix for the original data, there are actually differences in the variability. And that's what's, in the end, causes some differences in what the principal components end up being, and then, of course, then the corresponding variances. In the end, there's not much of a difference here. We can look at then the corresponding eigenvectors. So here is A hat 1 star. So we can interpret that. So PC number 1 is a measure of the overall size of the goblet with not as much weight, let's say, given to W6. You know, before we had the first principal component was, let's say, a measurement of the overall width and the reason why we were able to say that is because W6 had a value that was very close to 0. Here it is a little bit farther from 0. And so that's why I say, well, maybe it's just an overall size of the goblet. Principal component number 2. This represents the top of the goblet. Notice they're all positive. Here's the bottom of the goblet. We have some negative values. And then we have this W5 there, which was, oh shoot. What was it? The connection between the base and the cup. That W5 isn't really contributing much. So we see just a little bit of a difference than what we had previously. So negative values then of, oh shoot, let's see here. That should be a star there on that Y2. Negative values of the second principal component suggest that I have a large base relative to the cup. And positive values indicate a large top relative to the bottom. I have relative to the height. That just goes back to the, remember we originally adjusted the data for the overall height. PC number 3, there isn't really, I don't think a really clear interpretation of it. So now we can do some plots of the principal component scores and do some stuff similar to what we had before. The code's essentially the same as what I had before, so I'm not going to go over the code. We'll just look at the results. But I want to show you this little trick to get the PC scores to be what we want them to be. And that is, I can find, let's say, the standard deviation of W1, W2, W4, W5, W6, using the unbiased version of the estimate. And the way that I chose to do this, and we've seen the apply function before, where I say apply to all the columns in Goblet 2, other than the first one, which was just ID. Notice what's in red there. When I say all the columns, that's what margin equal 2 gives me. It says, okay, apply it to the columns. And the function I want to apply to each of the columns is the SD function for standard deviation. So when I do that, I'm going to get the standard deviation of W1, standard deviation of W2, and so on. Now, inside of PCA.core, there is a component of this list called scale. Scale actually corresponds to what R is referring to as the standard deviations. Without getting all the details, if you took a mathematical statistics course, you often refer to a standard deviation as a scale parameter, so that's where the name comes from. And so what I'm going to do is replace everything that was in scale before, which ends up being the standard deviations of the original variables, but the biased version. I'm going to replace that with the unbiased version. And so then when R uses the predict function, I don't even need that there. When R uses the predict function, it will now use the correct standard deviation when it finds the standardized values. Is everyone clear on that, or would you like me to re-explain? Re-explain?
Yeah.
Okay. So, when I find these scores, so y hat star rj is equal to a hat, let's try to write this again. Actually, let me just copy and paste it. That would be easier. Or we'll refer to this. Okay. So when I want to find a score, I need to know what the standardized values are. How do I find a standardized value? Now we'll just write it out. Value minus mean over the standard deviation, right? We want to use the unbiased version of the standard deviation. R instead will use the biased version. So I need to somehow tell R to use the unbiased version. And so if one actually looks at the corresponding code inside of predict to see how the actual calculations are done, you will see that R come back here. So if I look inside of names pca.core, oops, I guess I haven't actually executed that yet. You see something called scale there. Sorry. Okay. So when you originally run it, there you see scale. When I actually find the unbiased version of the standard deviation, I get this here. You can see that there's some small differences. That difference is due to using 1 over n versus 1 over n minus 1 in the calculation. Now, if one actually then looks inside the code to predict, you can actually see, and you don't need to do this, but you can actually see how it forms Z, the standardized values. And it will actually use this in its calculation of taking the value minus the mean divided by the standard deviation. So when I saw that, I thought, okay, I can do a quick little fix where I actually calculate the standard deviations the correct way, and I just simply put them back into that object.
Can you say again, what's the meaning of margin equals 2?
Yeah, true. So margin equal 2. I believe there's an example in the data distributions and correlation section where we work with the mean. Let's actually just use that. So let's say if I wanted to find the mean of each column, I can just use this segment of code, and this gives me the mean of each column. Now, how do I know it's a column? We have this very non-descriptive way of saying margin equal 2 means do it by column. So apply the function by column. If I were to, let's say, do that instead, now we applied it by row. Okay? Any other questions about this?
So why is the bias used in that?
I don't know.
Oh yeah, you said that.
I don't know. I don't know.
So is that like a standard practice then, is to
No.
do this?
Oh, standard practice. I'm sorry. Is it standard practice to use the bias version? No. Is it standard practice to fix it? Probably not, because I don't think people really notice it.
Okay.
It's just when I was teaching this a few years ago and I was trying to duplicate some of the stuff, things weren't working out. And so I had to actually then go into the function to figure it out. And it took many hours, unfortunately. Again, is it that big of a deal? No. If you want to do the fix, do it. If you don't want to do the fix, that's okay with me. We see, we have a somewhat of a small data set here. And you should try it on your own, with and without the fix. And you'll see there is some differences, but not much. These plots that we're going to look at here, they change just a little bit.
Okay.
And we only have a sample size of 25. Okay, so I can do a plot of the principal component scores, and this is what I get. And so, what we see here is somewhat similar to what we had before, but it's definitely not the same as what we had before. I would say it's maybe not as clear for what groupings could be. I still would put these together. Maybe I want to also put 18 in there now. I could put these together. Well, do I want to also include those? I don't know. Again, there's not always going to be a right answer. So there's the principal component scores, or scatter plot. Here's the corresponding bubble plot as well. And we talked about number 10 earlier. Notice where number 10 is now. It's above y equals 0 compared to what we had before. And let's actually take a look at it with respect to the coloring for positive and negatives. Now, it would be very questionable to use a third principal component here because it has an eigenvalue that's less than 0. But we can see here, look at 4, 17, and 5, and we thought, well, maybe we should put 18 in there. Well, we can see that it's let's say, big in a negative way in comparison to the 17, 4, and 5, which are much larger in a positive way. Also, we were wondering, well, what do we do about 22 and 10? Would we put those with 23 and 24? Well, we see some differences there. But we also see what we saw before, too, that notice we have a bunch of blue ones there, and we have a bunch of red ones down here. You could do a 3D plot and see some similar things as well. Let's see here. So this is what I came up with as a potential grouping if I were to use 3 principal components. If. Now, if I were just to use 2, which is probably what I would do, I might say, definitely these should be together. I don't know why maybe at least put those together. And it's questionable then what one would want to do, what one would want to do with these. These would be together, these would be together. We will look at more formal ways to make judgments about coming up with these groupings, not in the next section, but the section after it in our notes. But we will always come back to using principal component analysis to try to make sense of these more formal groupings that occur. And, also came up with some interpretations. For example, the red one, the red grouping is, well, we have these large overall in size goblets. Remember, the first principal component is more now a measurement of the overall size of the goblet itself. Okay, so let me now come back over here to the project. So with the data that you're going to use, again, what you need to do is show me that you understand, the material. So first part then with the principal component analysis, justify the use of the covariance or correlation matrix for the PCA. I expect that probably all of you are going to use the correlation matrix. And I'm going to repeat myself. Sometimes in teaching, it's good to repeat oneself. When one says, oh, I'm using the covariance matrix, or one says, I'm using the correlation matrix, this is standard terminology that people use. But again, when I say that I'm using the correlation matrix, that means I'm using the covariance matrix with the standardized values. Okay? So, make a judgment. We talked about how to do that. It should be really straightforward. I think at least of all the data sets that I've seen so far, you're going to be using the correlation matrix. So don't use that as a way to answer the question. Well, Chris said in class that all the data sets he's seen before, data sets he's seen so far, you're going to be using the correlation matrix. No, actually formally state why, based upon what we've talked about. Then, number 2, determine the number of principal components to use. So, what are you going to do? Look at the percentage of variability that's explained. I would use that as the number 1 option. We have these other things too that we have available to us that can also help. Number 3, try to interpret the principal components. It could be simply, this is a contrast between, let's say, x1 and x2 versus x3 and x4, while x5 and x6 don't play a role. Relative to my actual data itself, this is what this could mean. You might not be perfect in your explanation. That's okay. But I at least want to see an attempt to say what the different principal components are. Now, if you say, okay, based upon my data, I only need 2 principal components. Well, just interpret those 2. You don't need to interpret number 3. You don't need to interpret number 4. For your first experimental unit, first observation, and the first principal component, compute the principal component score. Do this using the predict function, but also show me how the calculations are done, let's say, by hand. So I want to actually see the equations written out. I want to see what the value for, let's say, Z1 would be, the Z2 would be inside this equation. Actually write it out. And as a way to, of course, check your answer, you could program in the equation into R and make sure that you're getting exactly the same thing as what predict gave you. If it doesn't give you the right thing, or the same thing, then you might be worried, well, maybe I've written out my equation wrong. I really like those kinds of learning tools because it really helps make sure that, yes, you understand how these calculations are done. You're not just, let's say, completely relying on a computer software package to do it for you. Number 5, create the appropriate plots of the principal component scores. Well, we've seen how to do some plots. Include interpretations in a similar manner as done for the goblet example. You might be interested in particular groupings. Or, you could also interpret, okay, the observations that fall over here correspond to observations that have this kind of a characteristics. The observations that fall over here on the plot correspond to observations that have these kinds of characteristics. Again, in the back of your mind, what you're trying to do is say, prove to me that you understand the corresponding material. Now here's a question for you. Let's say that you find 4 principal components are needed. How would you plot those?
first, for example, 2 by the third one, and the first 2 by the fourth one.
So you mean like, let's say do scatter plots where, oh, well, why don't you explain it to me again?
For example, for the bubble plot, we use the first 2 principal components, and that with the third one, and then another plot, the first 2 and the fourth one.
That is a possibility. I think it's okay. Let's say, okay, again, you have 4 principal components that are needed. I think it's okay to look at, let's say, a scatter plot, the first 2 only, to do a scatter plot of the first 3, or like a bubble plot. I think it's okay to do that, but then you just need to also say, I'm not maybe looking at all the information that I need to. So I would start there with essentially kind of what you're saying. I would not do a plot of 1 versus 2 with the bubble being the size of 4. I would want to keep everything in the same order, because remember they correspond to how much information is being explained. So I would do 1 versus 2 with the bubble corresponding to 3. But what else could we do to plot all 4 at exactly the same time?
3D and color.
Perhaps you could do some kind of, let's say, a 3D plot where maybe, let's say, a 3D scatter plot with the plotting point corresponding to somehow that 4th variable. But what's another kind of plot we could do?
Coordinate.
Principal coordinate plot. If you don't have too many observations, you could do a stars plot too. You know, there might be cases where you have 5 or 6 principal components. Okay, then you're kind of left with essentially one of these principal coordinate plots as maybe your only option. You know, so you can see how, especially now starting in this particular section, how things are relying on now the past sections. And in fact, you know, the stuff that we were doing in graphics, that's going to be all throughout the rest of the course. We're always going to go back to that stuff. Number 6, find the estimated variance of the first principal component scores from the actual data and match it with the appropriate estimated eigenvalue. But remember, the variance of y1 star should be equal to this, the first eigenvalue, if I'm using the correlation matrix. So what that means then is if I were to actually go through all my principal component scores, you know, let's say like with the serial data, we have 40 different observations. If I go with my, let's say, PC number 1, you know, I'm going to have 1, 2, all the way down to 40 of these values. Calculate the sample variance of those values. Okay? That should match up with what the estimate of that first eigenvalue should be of the correlation matrix. Verify that that actually does happen. Okay. So now you have enough background to complete the project. We're running a little bit late on time here. I apologize. So what's next in our class? I'll have office hours. I only will be able to do office hours, unfortunately, until 10 a.m. But if for some reason you need to contact me, please feel free to email me. We can set up a time to meet today, later today. We can meet tomorrow as well. On Tuesday, we will finish up principal component analysis. It won't be that much more. And then we'll also start a new set of notes called factor analysis. Factor analysis has similar goals as principal component analysis, but it's done a little bit differently. Looking further ahead, our project is due in 8 days, and test number 2 is Thursday, October 19th. Okay, that is all for today.